When you look at a modern marvel like the Burj Khalifa, this incredible needle of steel and glass just piercing the sky, it's so easy to just take it for granted. But that structure, it's the end result of literally thousands of years of trial, error, genius, and innovation. So, how did we get here? Well, that's the story we're going to unravel today. I mean, think about it. The journey from stacking these massive stones in the desert by hand to engineering towers that defy gravity. It's one of the greatest stories of human ingenuity, period. So the big question is, how did we make these incredible leaps in our ability to build? All right, so in this explainer, we're going to break this whole history down into a few key acts. First up, a time when we built with our hands and our eyes. Then, the era when we learned to build with formulas and math. And finally, where we are now, building with the insane power of computers. And of course, we'll end by looking at what's just around the corner. Okay, so our story starts way back in the ancient world, in what we can call the Age of Experience. For thousands of years, the challenge was really simple, but also incredibly profound. How do you create these lasting, monumental structures with no scientific theory, no calculators, none of the industrial materials we have today? The answer? You had to rely on what you could see and what you could learn from the people who came before you. So, the name of the game back then was something called empirical knowledge. This wasn't about calculating stress loads or anything like that. No, it was all about craftsmanship, intuition, and just generations of passed down wisdom. You'd build something, you'd watch it to see if it fell down, and if it stayed up, great. You taught your kids how to build it the same way, maybe just a little bit bigger the next time. And get this method worked for a crazy long time. We're talking about a period that gave us the Egyptian pyramids almost 5,000 years ago, the beautiful Greek Parthenon, and the massive Roman Colosseum. These were not primitive buildings. They were absolute masterpieces of logistics and geometry. Now, this is where it gets really cool, because you can see the evolution right here. The Egyptians, right? They mastered massive stone construction using geometry. The Greeks, they perfected proportion with their post and lintel system. That's basically just a horizontal beam on two vertical columns. But then you get to the Romans, and wow, they were the real game changers. They developed an early form of concrete, and when they combined that with the power of the arch and the dome, it changed everything. It allowed for aqueducts that could carry water for miles, and these huge open indoor spaces like the Colosseum that were just impossible to build before. But, building with stone has its limits. You can only go so high, you can only span so far. To break through that ceiling, we needed a totally new toolkit. So that brings us to our second act, the Age of Science. This is where the problem shifted from just building big to building smart. The big shift, the fundamental change, was moving from building based on experience to building based on calculation. Instead of just making structures super massive and heavy so they wouldn't fall over, engineers could now design things that were way lighter, way more efficient, because they could mathematically prove they would be stable. It was a total 180 in how we thought about building. Now, this didn't happen in a vacuum, of course. It was all powered by the scientific revolution. You had Isaac Newton's laws of motion, which gave us a way to describe forces. You had Galileo's work, which helped us understand how materials actually break under stress. And all of this was underpinned by advanced math that gave us the tools to put it all together. Suddenly, engineering wasn't just a craft anymore. It was becoming a real formal science. And this, right here, was the turning point. For the very first time in history, an engineer could sit down with just a pen and paper and predict, with incredible accuracy, how a structure would actually behave before a single stone was laid or a single beam was forged. And then, right on cue, the Industrial Revolution shows up and gives us the materials to match these new scientific ambitions. We're talking mass-produced iron and later steel. These materials were an absolute revolution. They were ridiculously strong for their weight, they were flexible, and you could manufacture them into pretty much any shape you wanted. This was the key that unlocked the modern world. So, with scientific principles in one hand and steel in the other, engineers started creating structures that would have been pure fantasy just 100 years earlier. I mean, think about the delicate, intricate ironwork of the Eiffel Tower, the soaring cables of the Brooklyn Bridge stretching across impossible distances, and of course, the steel frame skeletons that allowed the very first skyscrapers to rise up in Chicago and New York. And that brings us, well, pretty much to today, the digital revolution. The problem now isn't just about height or distance. It's about managing just extreme complexity, pushing for maximum efficiency, and making sure everything we build is sustainable. And the solution to all of that? Of course, it's the computer. So, how do we do it now? Well, the process is almost entirely digital. Engineers and architects create these incredibly precise 3D models using CAD, that's computer aided design. Then, they use this powerful software for finite element analysis, FEA, which is basically like a virtual stress test for the building. They can simulate everything from hurricane force winds to earthquakes. And finally, the whole thing is managed with BIM, Building Information Modeling, which keeps track of every single piece of data, from one tiny bolt to the entire electrical system. The digital world has also just supercharged the development of new materials. We're not just talking stone and steel anymore. The palette we have to work with today is just wild. We've got ultra-high strength steels, concrete that you can actually put under tension to make it stronger, lightweight composites, carbon fiber, and even smart materials with sensors baked right in that can report on their own health. And the results of all this progress? I mean, just look at this. The results are absolutely staggering. For thousands of years, the Great Pyramid was the tallest thing we had ever built. The age of science and steel comes along and more than doubles that with the Eiffel Tower. But then, the digital revolution with its computers and advanced materials allows for a nearly threefold leap on top of that to the Burj Khalifa. The growth here is just exponential. And this really gets to the heart of what modern engineering is all about. It's a huge balancing act. Yes, of course, strength and safety are still number one. But now, they're right up there with things like material efficiency, the long-term sustainability and environmental impact, and creating smart buildings that can literally monitor their own performance over their entire life. So where does that leave us? We've gone on a pretty incredible journey here, right? We've gone from the pure intuition of ancient builders to the precise calculations of the scientific age, and now to the powerful algorithms that run our world today. When you really boil it all down, each great era of building was defined by a totally new way of understanding the world. First, we mastered the physical world by just looking at it. Then we mastered it through mathematics. And today, we are mastering it through digital simulation. And that leaves us with one final fascinating question. We have built to the clouds. We've spanned vast oceans. We've created structures of just breathtaking complexity. So, what's the next great problem to solve? Is it building sustainably on a planetary scale? Is it creating habitats on other worlds? Or is it something we can't even imagine yet? That is the question for the next generation of engineers to answer.